So as soon as you are not able to hear me, you just make a call at that time only, okay? Because like otherwise that is wastage of time. I was speaking to myself then, okay? So you see, we have started like from in the last class we have seen this mass action law, and we have seen that the structure earlier we have seen the full structure, and then from this full structure we saw that we took the region under the gate only, and then we considered it as a two terminal device, okay? And for this two terminal device we first write the mass action law, and from this mass action law we can easily say, or can like write that this the we can determine the concentration of minority charge carriers and the majority charge carriers, that is p0 and like n p0, okay? So minority charge carriers are in p-type material, the minority charge carriers are electrons, whereas the majority charge carriers are holes, and that majority charge carrier depends upon the doping concentration, okay? So that was it. And then from this you can see in the previous class probably we have seen this, but not in complete detail. So let me tell you that whenever you dope the material with some trivalent type of impurity, then the material becomes a p-type material. So in that case your Fermi level, I mean at the absolute temperature or the intrinsic material, if it is an absolute if at an absolute temperature, the intrinsic level and the Fermi level are at the same level, okay? But if the temperature if the material is at the room temperature, then because of the temperature the there are some charge carriers into the material, so the Fermi levels get shifted. Either if you dope it with the some I mean in the intrinsic material also, the Fermi level will be different from the intrinsic level in case of I mean at certain room temperature or temperature above the absolute temperature. But if you dope intentionally with certain impurities, then obviously the Fermi level shifts in certain direction, as we have discussed in the last class. So in case of trivalent impurities, the Fermi level shifts towards the valence band, whereas in case of pentavalent impurities, the Fermi level shifts towards the conduction band. So for this type of materials, if you just want to, I mean for these materials, whatever material they are, whether it is a semiconductor material or a non-metal or something, so whatever type of material it is, we define certain parameters for it, and based on those parameters we also some I mean compute or calculate some other parameters also, which are required to understand the transfer of electrons from one level to the another level. So this whatever we are going to discuss in this formula, which are written on the this right side of the this slide, so that I am going to explain. And this all formulas are based on, I mean are required for your energy level, the energy required, or the I should say the energy required to move the charge carriers from one level to the another level, okay? Because there are many levels which are involved into the material, okay? Right from the valence band to the conduction band, in between there are many levels, energy levels. So how to define these energy levels? These energy levels are defined like first one you can see that phi f is defined. So phi f is nothing but your this term particularly is called your Fermi potential, okay? F is written, so Fermi potential. If it is phi s, then it is surface potential, okay? So phi f is written, so you define it as Fermi potential. So what is your Fermi potential? So Fermi potential is basically nothing but the amount of energy. It is like energy divided by charge, okay? So that is what you define as Fermi potential, okay? So what energy difference you will take? So this is energy difference, I mean the energy required to move the charge carrier from the Fermi level to the intrinsic level in case of p-type material, whereas in case of n-type material the equation will be just opposite, ei minus ef, because what you are saying is, I mean in case of the definition for the Fermi potential, the definition for the Fermi potential is the amount of energy required to move the charge carrier from intrinsic, to move the charge carrier between the intrinsic level and the Fermi level, okay? So if the intrinsic level is at higher level, so then you will take the difference of Fermi level to the intrinsic level, whereas if the Fermi level is higher than the intrinsic level, then you will take the opposite, Fermi level minus intrinsic level, okay? So that is what we do. So Fermi level minus intrinsic level or intrinsic level minus Fermi level. So if, I mean, the definition is from Fermi level to the intrinsic level. So if it is like in case of n-type material, the equation will be just opposite. So it will be minus will come. Okay, and if you just write the equation for EF and EI, okay, in case of the what we define as the Fermi energy. So if you write that equation is like you have studied in physics. I mean, I could have shown you that equation here, but I have just skipped that equation. Okay, and like that is not in the PPT, this PPT particularly. But if you want, I mean, I'll let you know that have like this integration term in that equation. So that equation I'll let you know later. And I also don't remember that equation, so I cannot like reproduce it right now. Okay, so that energy level equation, if you write, so this equation will give you Fermi potential something like kT upon Q, this log of Ni upon Na. So Ni is your intrinsic intrinsic charge carrier concentration, and the Na is the doping concentration. Okay, so in case of Fermi, I mean, if you want to define the Fermi potential for your n-type material, then the equation, the logarithmic part will be like opposite. Okay, the part which is outside the logarithmic, the constant part will be same, but the part which is inside the logarithm, then it will be opposite because of the minus sign, the definition which is there. So that is what it is. And apart from that, you can see other other levels as well in this diagram on the right side, on the left side of the PPT on this slide. So you can see that there are some other levels are also defined. So what are these levels? So one level you can see is like Q psi. Okay, so charge into psi. So what is this? Q psi is basically, they are all like energy. Okay, so they are all energies, energy per charge, per unit charge. Okay, so Fermi, this Fermi potential, what you have defined is energy difference per unit charge. Okay, so here this what you define as Q psi is nothing but the electron affinity. And from this diagram only you can understand that electron affinity is nothing but the amount of energy required to move the charge carrier from conduction band to the vacuum or to the free space. Okay, so that is what your this Q psi or the electron affinity is. And why this will be required? As I have told you, this will be required to define certain other things. Okay, to determine like how much energy will be required. So the aim of the this particular lecture which we are taking, this 2 lectures, the last lecture and this, is to determine the threshold voltage. Okay, so we want to determine the threshold voltage. So to determine the threshold voltage, we just want to know like on what parameters it depends upon. So to know that is why we are defining this thing. So remember that the aim, keep this aim in the mind, that why we are studying all those things. Just don't lose that. Okay, that aim should be clear, that why we are studying this. Okay, so you see this Fermi level, this electron affinity I have defined, whereas you define the Fermi potential as in the diagram you can see Q into phi Fp. So this is called your work function. So Fermi potential into charge will become your work function. So that is also the energy difference only. So this is like the amount of energy required to move the charge carrier from Fermi level to the intrinsic level. Okay, sorry, there is some like mistake in this. So this is not the work function, is like Fermi level to the free space. Okay, so when you move a charge carrier from conduction band to the intrinsic band, then it is called this, I just forgot it, so let me see it once, that conduction band to, because there are so many terminologies, so people might forget it. Okay, so okay, so that is like I'm not able to, I won't be able to find it so quickly. Okay, so let's assume that this is also certain energy. This Fermi level to, okay, that is Q phi Fp. So this is like I have defined this Fermi potential. So Fermi potential into charge. So that is what the energy difference is. So that is what we have defined earlier. Now let's move on to, this is we have seen for a single material. Okay. Now, if you combine, because in case of MOSFET, when you have seen the this two terminal structure, there are 3 type of materials which are connected together. So this is like metal, which is aluminium. Okay, in case of, you can use aluminium or certain other material. So let's consider for first of all, let's say this aluminium. Then there is an silicon dioxide. If you are using a silicon, if you are using silicon as the semiconductor, then there is silicon. So the energy band levels will be at different levels. So you can, I mean, in the last class I also have told you, you can consider them as potential energy levels, okay, potential levels, potential energy levels. So you see these energy levels are at different heights. So if they are at different heights, so then obviously there will be some energy difference between them. So you assume that initially the vacuum is at the, the vacuum is at the same level for all the materials. Then corresponding to that, you draw the Fermi levels for other materials. So for metal, the energy difference between the vacuum and the Fermi level will be least. So that is what it is drawn here. Whereas in case of oxide, the difference between the conduction band and the valence band will be very high. Okay, so that is also shown there. Whereas in case of semiconductors, the energy difference between the conduction band and the valence band will be lower than that of the oxide. Okay, whereas the conduction band and the valence band are overlapping in case of metals. Okay, so that those all things are shown here. And apart from that, you can also see that in the semiconductor, the same things which I have shown you earlier are shown here as well. So the levels for these materials, this this various parameters are also defined, whereas like q phi m, which is defined as your, I just forget them, so let me see it once again. So this q phi m is your Fermi potential. This is like okay. So this we define basically as your work function. So work function is nothing but the amount of energy required to move from Fermi level to the vacuum. Okay. So if you take the difference of this energy level from Fermi level to the vacuum, so then it is called your work function. So you see the work function for metal is basically 4.1 electron volt, whereas the work function for oxide cannot be shown directly. Okay, because you cannot see the Fermi level in this diagram basically, but it will be something like the electron affinity, which is q psi, which is given like here, 0.95 electron volt for silicon dioxide, and then you will have to find like valence band to conduction band. Okay, the energy difference between the valence band and the conduction band you know as 8 electron volt. So if you want to find the work function for it, so then you have to compute it corresponding, I mean, using these things. Whereas in case of semiconductor, if you want to find, so then this work function, which is denoted here as q phi s, okay, this work function, and this is for your surface. Okay, so you define it as surface potential. Okay, when the work function is defined particularly for a surface, because you see we are like, this is like at the connection of the surface, at the surface of the, at the boundary of the semiconductor, oxide and metal we are talking. So for this surface potential, if you define, so then it will become q phi s, and that will be this electron affinity for semiconductor, which is 4.1 this electron affinity, which is 4.15 electron volt for semiconductor, and this EC minus EF. So conduction band minus this Fermi level band. Okay, so Fermi level is something different. So you know that in this case somehow we have to compute, because we know that the difference between EC minus EV is 1.1 electron volt. The band gap between the very popular known figure, the difference between the valence band and the conduction band for for the silicon is 1.1 electron volt. So if you know these things, you cannot directly compute the work function, but you have to compute something in between as well. Okay, so this thing whatever is there is in between, so that also we have to compute. So let's see, I mean, how we will compute this and this work function. So this work function is an important parameter, which is the amount of energy required to move from Fermi level to the vacuum. So that you keep in mind, and that also we have to find. So there are, like in the book you will find that the things are explained with the help of energy band diagram. So you see what will happen, energy band diagram, as I have already explained you in the last class, that the energy band diagram and the band bending comes because of what? Because there are, whenever there are different materials connected together, then there will be always this work function difference between the materials. Okay, the energy levels will be different, and as you have seen in the last slide, there is like difference between the energy levels of various materials corresponding to with respect to your vacuum. So then obviously there will be some work function difference as well. Okay, the work function difference between the materials, because the amount of energy which will be required to move from the Fermi level to the vacuum will be different for different materials. Okay, so that is why there will be work function difference. That is what is called the work function. So work function will be different for different materials. Okay, and I mean, if you'll just see between the two materials, then also there will be some difference between these energy levels per unit charge. So that is what you call as work function difference between the materials. Because of this work function difference, what will happen? The bends will bend, okay, near the surface. They will be like there will be no bending in the bulk of the material, but at the surface, near the surface, there will be some bending in the energy bands. Okay, and that bending is in the direction of the electric field. So that is what we have seen in the last class. Okay, and you see, I mean, so as they are in the direction of the electric field, so in this diagram you can easily see that if you just consider the metal on the one side, then oxide on the other side, on the in between, and the p-type material on the other side, then you can see that the bends are bended towards the Fermi level of this material, because the Fermi, when you connect them together, then the Fermi level we will consider the Fermi level at the same level, at the same energy level, and corresponding to that, if you just draw the other energy levels, then you see in this material, particularly the electric field, when you don't apply any voltage, the direction of the electric field will be, because I mean the direction of the electric field will be what? The direction of the electric field will be, you see, this p-type material is like there will be some negatively charged carriers here. So negative charge here, and as you have not applied any charge on the metal, so the electric field will be as like the electric field is like the direction of the in which the positive charge moves. Okay, if you let the positive charge, a unit positive charge, free to move in any direction, so then in that case it will move in the direction of the electric field. So here in this case, the electric field will be directed towards the silicon. Okay, so it will be from metal to the towards the silicon. Okay, so you can see the direction. So as you can see that the direction is in this way. So you see the as you move from the metal towards the semiconductor, the bends will move in the direction of the electric field. So that is what you can see. So that is what it is. And corresponding to this, like how much voltage, or I mean how much like energy will be required to make this bends again flat. So that is what is defined as that is what is called as flat band voltage. Okay, and how you define this flat band voltage? It is the difference of the Fermi this metal Fermi the surface potential, this Fermi potential for your metal, and the surface potential, because you see the this is like work function difference. Okay, so this particularly this energy band bending is taking place because of the work function difference, and this is what you are subtracting to get the flat band voltage. Okay, so one is higher and the other one is lower. So how you define the flat band? So that is the amount of voltage which is required to make the bands again flat. Okay, which is like bended. So whatever amount of voltage will be required to flat the bands again will be called as flat band voltage, and that is defined as the difference of the work functions between the two materials. Okay, which whatever you are connecting. So metal and the semiconductor here. So that is why it is written phi m minus phi s. So phi s is the surface Fermi potential for your this surface potential you call it. So surface potential for your semiconductor. Okay. So this was it, and you see, so earlier when you have not applied any voltage, so then the direction of the bends was as I have explained. But in case of when you apply some voltage on the conduction on this gate of the material, so and that voltage is, let's say, negative voltage. So then what will happen? The if you apply some negative voltage, and that too is very small. Okay, so then what will happen to these bends? How they will move? Let's see. So when you apply a negative voltage on the gate terminal, then the direction of the electric field will be reversed. Why? Because the holes will get attracted somewhat, whatever number of holes are present, because the holes are majority charge carriers in that, then this p-type material, so they will get attracted towards the surface. And because the holes are attracted in this direction, so the direction of the electric field will be reversed. Okay, because it will, now if you move if you let a positive charge carrier to move, if you let the positive charge carrier free to move in any direction, so it will move in the upward direction. Okay, because it will be repelled by the holes. Okay, so the direction of the electric field will be in the upward direction, so it is reversed. So now as it is reversed, you can see that the bends are again bended. Okay, so the bending is like in the it is also changed. Okay, and you can see that this particular thing is like reverse biasing. So when you reverse bias, so what is happening, you are increasing the energy level. Okay, so the difference between the two energy levels you are increasing. Okay, so that is what is happening. So you can see the bands are again moving as you are moving from the semiconductor from towards the metal. So the bands are moving upward in this case. Okay, this way you can see, or otherwise if you see in the opposite direction to the electric field, then the bands should move downwards. So if you will move from metal to the semiconductor, then near the surface you will find some level, and in the bulk of the material, in the depth of the material, you will find the energy levels little lower. Okay, the levels of the energy will be lower. So that is what you can see. And here also you can see that the difference between the intrinsic level and the Fermi level is again, in case of metal, it is increased because you have applied a negative voltage. Okay, so that all depends on this. And now you see, so basically what we are doing, we are trying to see that when we are applying different voltages to the gate terminal, then how the material is responding. Okay, and how the energy levels are shifting. So earlier we have seen that how the material was looking when no voltage was applied. Then we saw that when a small voltage is applied, okay, then what happens? So that phenomena is called accumulation. So we'll revisit this particular things in a different, we'll try to understand these things again in a different perspective, in a simpler way in later classes. Okay, when we will understand the operation of the device. At that time I will try to explain you once again, but I want to just explain this energy level, the explanation with respect to these energy levels also, because in the book you will find this particular thing explained very in depth, and this particular thing is also important when you move on for your higher study. So at this level, these things should be clear to you at least. The terminologies, if you forget, then it is not a matter, you can revise them, but the concepts one should be clear to you. So that's what the point is. So that's why I'm trying to explain. And I understand that this time you may feel that this particular explanation is not connected with what we are doing. Okay, but later on you will see that this all is connected when you will derive the threshold voltage equation. So you see, as we are changing the potential at the gate, the potential at the gate, so then what is happening? The whatever is happening near the surface is also changing. So when there was nothing was applied, some situation was there. Then later, when you have applied a negative voltage, then there was some situation. Now you are applying a positive voltage, okay, but a small quantity. Okay, again. So then what you will see, the direction of the electric field is again reversed. Now the direction of the electric field is again reversed, and simultaneously, because this you have applied a positive voltage on the gate terminal, so then what will happen? The positive charge lying near the surface in the substrate material, and this p-type silicon and this p-type substrate will get repelled into the bulk of this material. So then what will happen? A depletion region will be formed. Okay. So when you apply a negative voltage, accumulation region is formed. When you apply a small positive voltage, then a depletion region is formed. And in case of depletion region, again you can see that because you see this is like forward biasing. Okay, so now if you are forward biasing, so then the difference between these energy bands, the Fermi level and the intrinsic level will also change, and you can see the band bending. So again the direction of the band bending is changed. Earlier, when you applied a negative voltage, they moved in the upward direction near the surface, and now as you have again applied a negative voltage, then it is moving in the lower side. Okay, and as the situation is different from the case when you have not applied any voltage. So in that case, the intrinsic level was little higher than the Fermi potential at the surface, if you will see, for the p-type material. And when you see, I mean, when you apply this small voltage, the small positive voltage, then you can see that in the material, in the complete this MOSFET, if you will see, in the complete this NMOS, if you will see, then you will find that this a depletion region is formed in between, underneath the gate. Okay, and the depletion region is also formed somewhat under the source and the drain region as well. Okay, whereas you can see that the source and the gate region are completely, both of them are like completely grounded, whereas the gate terminal is like connected with certain voltage but a very small voltage, and that small voltage, how you define that small voltage, is actually the voltage which is less than the threshold voltage. Okay, so if you increase the voltage, if you keep on increasing the gate voltage, and if it increases beyond a certain level, which is like, which will be defined as the threshold voltage, then you will see something different. So we are increasing the gate terminal voltage, but it is lower than the threshold voltage. So we want to see that, I mean, how much this voltage will be required. So then we will be able to see that what is the threshold voltage. Okay, so you see, hope the things are clear, or is there any doubt up till now?
Sir, more in-depth study is required.
I mean, are you able to
from our side?
Huh? Sorry?
Sir, I'm not able to relate from the previous things I've studied, so yeah.
Previous things, I mean, have you not studied these things particularly?
Energy bands, we did, sir, in the first semester.
In the first semester, in fact, in class 12th also you might have studied these things.
Yeah.
Isn't it? Energy bands and all those things. Okay, but you've not studied this band bending particularly, I think. Have you?
Sir, yes, sir. That's in MOSFETs, like particularly the metal and semiconductor interface. Sir.
Right.
That's the new thing.
That, and because you see, in analog electronics, electronic devices also, Milman Helkias, if you'll pick, he has explained everything in chapter 1. Okay, there's all things. Chapter 1, chapter 2 most probably. So it's not like you have not studied them completely, but you have not studied it with respect to like how they are used to form different like devices. Okay, so that is why I'm like trying to emphasize it, because later on if someone picks the this particular field of like device studying the devices, electronic devices, then this particular things are very important, becomes very important. So that is why I'm trying to explain you. And you see, probably you may not be able to understand it, but you know that these things are important and you have not understood it, and they may be asked in the exam. So then you will at least go once, you will just see them in depth once at least. So that is what the purpose is. And if you have not able to explain, you can ask me. I'll try to explain the things. Okay. Okay. So move on. Let's try to move on, and I'll clarify your all the doubts. I mean, if you have any after the class. Okay.
Yes.
Fine. So you see, so in the this particular, in case of this material, this depletion region is formed. So now you see, we will try to see that this complete depletion region up till the time, I mean, the depletion region is formed. So how much voltage will be required to form this depletion region? Okay, because you see, in the depletion region, what will happen? Some positive, some negative ions will be exposed, isn't it, in the depletion region. So when you are calling it depletion, so it is depleted of the charge carriers. So earlier there were like holes everywhere, but now as you have applied a small positive charge, so then what will happen? All the holes will get repelled. So a depletion region is formed. So how much voltage is required to repel those holes? Okay, completely near the surface. So that much voltage you have to find. So that voltage is basically depends upon the doping concentration, the amount of charge carriers which you have, isn't it? More, more doping you do, more voltage you will require to repel those. Less voltage you will require to repel this. Or if you do less doping, then more voltage you will require to repel them. So something like that. Okay, so let's see how this particular things will turn out. Okay, so we want to find this, how much voltage is required, or how much is the amount of charge which is like there because of the ions. Okay, so depending upon the charge ions, we will see that how much voltage will be required. So the first thing is like how much will be the charge because of this exposure of the ions, okay, underneath the surface. So let's try to find that. So how to find it? So to find it, we use the Poisson's equation, because this is sort of continuity equation. So we are like moving from one material to the another material, and you want to see that what is the continuity. So you have to use the Poisson's equation. So the reason is like you people may ask like why the derivation is started with the Poisson's equation. Okay, so the Poisson's equation is like one of the continuity equation, and this particular thing also helps you to determine the surface potential, okay, with respect to like your charge density. So how this is defined? So this Fermi potential, if you know from your previous studies, so then the Poisson's equation is this surface charge density divided by the this epsilon of the material. So that is your dielectric constant. So then if you use this, if you just if you want to determine the Fermi potential, surface potential for this material, okay, so then what we do, we integrate it, differentiate it, and differentiating on the both the sides, we write that equation as dq upon epsilon si, because we are doing it for silicon. Now the purpose is like to find what is dq, because the surface charge density is nothing but q into x, q into the length, right? So x is the length of your depletion region and dq is the amount of charge carriers there. So we have to find that what is this dq is, isn't it? So dq depends upon what? Q into Na into x. Now you see, sorry, x is not the length, but it is the depth, basically the depth of this. Yes, this is the depth of the depletion region. So actually we want to find the depth, because you see the charge carriers will be stored in the in the layer, but there will be some layer, okay, some depth of the charge carriers as well. So we have to find this particular this what are the amount of this charge carriers into that. So how to find this? So let's start with dq. So dq, if you just write it, so it will be q into Na into dx. So you just integrate these things and you will find that from this equation that the depletion region depth, okay, depth of the depletion region will be given by this equation xd. So if you just integrate the equation, you have the basic equation. Now you want to find the value of xd, okay, the depth of the depletion region. So how you will find the depth of the depletion region? You will do some manipulation corresponding to that. You will substitute the equation of dq in that above, equation, above equation, this equation I'm talking, and then this particular is the equation of your dq. So substitute this in this, and then to find the dx, what we do, we have to integrate it, right? So we have integrated it, and the equation is written in terms of xd square. And if you just find it, so this is the equation for your xd, and this equation is again important, okay? So xd, like how much is the charge depletion, the depth of the charge region, because you know that per unit surface charge density is like your per unit surface charge density, okay? So per unit surface charge density you know, but then if the material is having, if there is like no depth, okay, so it is just on the surface, on the first topmost layer, then it is okay. But if it is having some depth, the depletion region is having some depth, so there will be some charge carriers in that depth also, so you have to find the depth also. So that is what the reason is. So the depth will depends upon how many things? It will depend upon the difference of the surface potential and the Fermi potential of the material, okay? So phi s minus phi f, it will depend upon, also depend upon the, inversely it will depend upon the doping concentration, okay, and it will also depend upon the dielectric constant of the material, right? So these are the few things on which your depth of the depletion region depends, right? And if you just substitute this xd into the equation of q, so then you will be able to find that what is the amount of charge carriers because of your immobile ions, right? Is it clear? Particularly this thing, that how you find out this.
Sir, like when we are talking about the immobile ions, so and sir, or the depth of the depletion region, so we are talking in the sense of surface, between the SiO2 level, that's silicon, and that P channel,
Yes.
or so we are talking about the source or drain and
No. We are not
gate
talking the region under the source and the gate region which is depleted. We are talking basically about the region which is under the gate, right?
under the gate. Yes,
Under the gate.
yes,
Okay.
because there is also like source and channel is also depleted when we applied like potential, because
They will be
that's also
depleted
P.
up to some extent, but their complete depletion. I mean, at this level, because the source and the drain are like at zero potential. Okay, you have not applied any potential there. So to calculate the depth of the depletion region in under the source and the drain region, the method will be same, but you have to use the potentials which you have used there. Okay, on the source and the drain terminal, right?
Yes, yes.
Okay, so we are trying to find that whenever you have to find the depletion region, okay, then what is the method actually? How to find it, right?
Oh,
Later on, we will use at that. Okay, later on you will see that how to find that as well. When we will compute the capacitance, okay, that time we will use that. Okay.
yes, so basically, like in the case of NMOS, like P channel substrate, so we are applying the positive potential so that we can develop a depletion region, because like here electron are the minority charge carriers, and
Right.
in a P channel substrate, that holds a majority charge carrier. So
Right.
we are trying to bring the electrons in the channel,
Very right.
which is a minority.
Very right. Okay, because this is an n-type material, so we are trying to. The aim is to bring the electrons from source and drain. Okay, so first you have to deplete the surface, right?
Yes, which is like majority in holes. So we don't want holes in the channel.
Right.
We want electrons.
Electrons in the channel. So we have seen that if we apply the negative voltage, then what happens? If we apply a slight positive voltage, then what happens? And if we keep on increasing the voltage, then what will happen? Actually, at the surface, because the surface is of the topmost interest.
Yes, yes, yes.
Okay, fine, clear.
Okay.
Let's move on. So for this, this particular things I have already defined. Okay, and we have seen that the depletion region thickness is basically given by this formula. Okay, and this is important. Remember this. This will depend upon your surface potential, Fermi potential, and the doping concentration and the dielectric constant of the material. Okay, we have also defined the work function and we have also defined the flat band voltage. I have already explained you these things. Okay, and we have also seen that the accumulation and depletion region. What happens when accumulation region is there, when depletion region is there. When your Vg is less than 0, and when Vg is greater than 0, then what happens, right? And your body Vb is is at 0 potential in both the cases. It is grounded in both the cases. Okay, so that is what it is. Now let's see. So this is also we have seen. Now the point is what will be the maximum depth? Okay, so first we have seen that the depth will vary depending upon your voltage applied. So what will be the maximum depth? So maximum depth of the depletion region can be found by the same equation, but in that equation what you have to do, you have to substitute phi s equal to phi f. Why? Because you see at this particular instant this equation will get its maximum. Okay, and the surface will be completely depleted at this particular when your surface potential is exactly equal to the is exactly opposite of the Fermi potential. Okay, so whatever is the Fermi potential, so that much voltage can be developed at the surface, not beyond that. So that is the maximum limit of that. So to find that in this equation, what we do, we just substitute phi s is equal to phi f and then recompute it, and we see that the maximum depth of the depletion region can be this much, right? Okay, and at this particular instant what will happen when your Vg is increasing? So now you see this Fermi level, the central, let's see the first diagram first. So here you will see that what is happening. I mean, this is the last slide, and then we'll discuss the remaining in the next class. So you see what is happening here actually. As you keep on increasing the voltage, the field of the direction of the electric field is same. It is not changing. It is the same when the Vg was less, I mean positive, but small value. So the direction is same here also. But now the intensity of the electric field will increase. So now with increase in the electric field, what will happen? The bending near the surface will be more, right? And as the bending will be more, so then you see what will happen. Why I have told you this minus f? Because at minus f, you see the difference between the VFP in the center diagram, in the middle diagram, if you will see the difference between the EFP, the energy level, the Fermi energy level, and the intrinsic level is what you have defined as the work function is phi f. Okay, this maximum you can reach there also, because you see between the valence band, I mean, then you will, after that you will reach into the valence band. So the maximum band bending can be this only. Okay, so 2 phi f. So I mean, in different ways you can understand the same thing. So what is happening here is at this level, the charge carriers, you will be able to, now at this level what is happening, you are able to attract the electrons from, I mean, as you have not used the source and drain, whatever the minority charge carriers were present into the material, you are able to attract them near the surface. So you see your surface is inverted now. So earlier the positive charge carriers were accumulated near the surface when you applied a negative voltage. Then when you increase the potential, then the charge carriers were got depleted near the surface, and then now it is inverted. So at the inversion, what is happening between the energy levels? So the energy level is like now again shifted more, okay, near the surface, bended more near the surface. So the bending is more near the surface in this case. Okay, and the maximum depth, you can find that the previous formula which we have seen is this. And at the surface the situation is, now you can see, though the gates and the drain terminals are grounded, but the inversion layer is formed now. So this is what will happen. Okay, the inversion layer in this case will be formed if you have the source and the gate terminal, drain terminal. So then the charge carriers will be attracted from there, or either if they are not there, then the charge carriers will be attracted from the bulk itself. Okay. So I hope this particular discussion is clear to you now, and these things we will discuss in the next class then, the remaining things, physical structure, and moving on to the other things, because the time is almost over. You may be having the another class then. So is that okay?
Okay, sir.
Okay, so any doubts?
Okay, sir.
I hope the doubts Abhinav has asked, I mean, in between, and were able to clarify the things. After that, the things were more clear to people. Or any other doubt?
Sir, actually, I think we have to go through these things more deep, and then we can ask doubt.
Okay, so you just, do you have the book? Have you got the book? All of you?
Downloaded, sir.
Downloaded, na? Okay, so I have shared it with Madhura, and I've asked her to share it with you as well, all of you. So if you have downloaded it as well, these things you will find in the book. So just go through it, and not only the book, you can go from, you can refer some other books as well. As I have told you, Milman Halkias. So in Milman Halkias, you will not see the discussion with respect to the MOSFET, but you will see the discussion with respect to the PN junction in chapter 1 and chapter 2, as I remember. Okay, so go through whatever book you want to, and then probably in the tomorrow's class or later on, whenever you want to ask, we will try to clarify those things. Is that okay?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Fine. So let's stop the today's class here itself then. Okay.
Okay, sir. Thank you, sir.
Okay, fine. Thank you.
Okay, sir. Thank you.
Thank you. Thank you, everyone. Let's meet tomorrow then.
Okay, sir. Thank you, sir.
Okay, thank you. Why I'm not able to disconnect it?